Okay, so let's start. So the subject of today's lecture will be again Keynes equations. Okay, for a system of rigid bodies. So let's recap where we were at during at the end of last lecture. Is it? Can you see from remote?
Yes.
Okay. So let's recap. So the first result that we were able to derive was that the virtual work, the total virtual work, could have been expressed as the sum going from I equal to 1 to MB, where MB is the number of the bodies of our multi-body system, and J going from 1 to N, where N is the number of generalized coordinates, of Fi, where is the force resultant equal to the difference between the resultant of external forces and the rate of the momentum, times the derivative of the velocity with respect to the generalized coordinates Qj. This, of course, had to be equal to 0. Okay? So this was the first. Then we introduced the motion parameters in the following way. So we had that the generalized velocities Qj dot were expressed as the sum with m going from 1 to the number of the coordinates of AJM UM plus BJ, where basically these UM were called generalized motion parameters. Okay. It was just a way to basically describe our generalized velocity as a linear combination of the motion parameters. Eventually, at the end of last lecture, we were able to express the velocity of a, let's say, of a body I expressing with respect to the inertial frame as the sum from m going to 1 to n of the vector v m I with an overhead times u m plus v t I with an overhead. Okay, where again we had basically the appearance of the motion parameters. So basically this is the velocity vector of a body I within our system expressed in terms of the motion parameters. Okay, so these were basically where we were at last time. So today what we're going to do is to insert inside our formulation the constraint equations. Okay, so let's do this. So let's express our constraint equations in terms of the motion parameters. So constraint equations. in terms of the motion parameters. UM. Huh? Well, so again, on this point, I would like for you to remember that both for the non-holonomic and the holonomic case, we can always put our constraint equations in the kinematic form, okay? So we can always express, this is a small recap, so for both non-holonomic and holonomic constraints, you can write basically our formulation like so. Okay. Yeah. Here. No. This is just nothing to do. Yeah, you're correct. So, I mean, this is, this is I recall just the formulation that we used before. Okay. But these are general, let's say, names. They do not relate in any way to this one here. So if you want, you can call this B small, okay, or whatever. Just not to make it, if you want, not to make confusion. What do you mean, second order?
There are two bodies starting at the same angular velocity, and I want to maintain them at similar angular velocity. Can I put a constant in angular acceleration?
Yeah, of course you can. Sure.
And then the formulation is
Non-holonomic. Yes, of course, because in that case, again, you have to use the augmented formulation that we have described last time in order to include this constraint equation into your formulation. Yes, of course, there are conditions that you can have on the acceleration. Yeah. Right? But typically, this is not something which is very usual, because, as you can imagine, your equation of motion, they are expressed in terms of forces, okay, which are there. So they are equilibrium equations that encompass within themselves motion parameters, or in general kinematic entities, so that you pass from equations of motion, from equation of equilibrium, which are described in terms of forces and torques and everything, to equations of motion which predict the motion of a part in terms of those quantities which describe their position and orientation in time. Okay, so this is the thing. And typically, since you start from forces and torques, and then you arrive to a motion, so in displacement and angles, you typically have second order derivatives with respect to time of displacement and angles. That's to say acceleration. This is, the typical example is F equal minus k times x double dot, which is the spring, okay? So since you start from an equilibrium, okay, you end up having second order derivatives. So your typical equations of motion is expressed in terms of second order at maximum, part derivative with respect to time. That's why you don't expect to have condition on the second order, but on lower orders, okay? Because if you have a second order equation of motion, the differential equation of motion, you have condition on what? On velocity and on displacement, right? That's how you do it. You don't have condition on the higher or highest order of derivation. Okay, that's actually the equation of motion. Okay, that's why you typically don't get constraint equation in terms of acceleration, but typically in displacement and in velocity. Okay.
If I understand you, because
The equations of motion derive from equilibrium equation. The equations of motion, like we have actually done last time, okay, they are equations expressed in terms of displacement and rotations, but they derive from equilibrium consideration. They are not, written starting from, some abstract principle. They do enforce an equilibrium. Okay, they are the transcription in terms of motions and rotation of equilibrium. Okay, so that's why they typically show up to the second order time derivative. Okay, so if you have a second order time derivative differential equation, okay, your conditions are not on the highest order of differentiation, they are on the lower, n-1, right? So if you have to solve, even in common mechanical problem, if you have to solve a problem with a partial differential equation with respect to time up to second order, you get condition on what? On the displacement, on the velocity, right? Plus, of course, the initial condition. Okay, that's why you don't get constraint equation in terms of acceleration, but possibly you can. But you can have it, for example, in terms of initial conditions, not in terms of a condition a constraint equation which is enforced throughout the motion. Okay, so it's a starting position. You can have, the acceleration starts with this velocity, with this value or orientation or direction. Okay, sure. All right, so okay, we have changed this way of indicating the constraint so that it generates no confusion. What I wanted to stress out was that, again, the important point here of Kane formulation is that it enforces the constraints via the definition of velocities. And this is something that can always be done for constraints equations. Okay, you can always express them in terms of velocities, while the converse, express them in terms of displacement or the q's of generalized coordinates q. That's not always possible. For non-holonomic constraints, it's not possible. Okay, all right. So it means all of this means that we can always write our constraint equation in terms of the generalized motion parameters, um, because the um are velocities. That's what I wanted to show you here. Okay, you see, your motion parameter is nothing else than a linear recombination of the generalized velocities. So they are velocities as well. Okay, so that's why, since they are velocities, you can rewrite your constraint equation in terms of the UMs. Okay, and they do write like so. UM is equal to the sum of S going from 1 to the number of independent parameters ni, of what? Well, we can call it C, MS, US. Okay, plus D, M. Okay, so these are the constraints equation expressed in terms of the UMs. Okay, all of them, both holonomic and non-holonomic, can be written like in this way. Okay. Okay. Now what we have to do is to include this constraint equation in our formulation. Okay, this is our goal. So we can do it. And let's go to another page so that we have enough space to go on. So our p dot I becomes well, so we start basically from here, no? What I'm saying is that this is our p, p dot I. We have to insert here in the expression of the the constraint equation, okay, that we have just written here. Okay, so let's do it. And let's see how it goes. So this is the sum of m going from 1 to ni, where again ni is the number of the independent, so it's the number of degrees of freedom. Okay, to cut it short. That's the sum of m going from ni plus 1 to n. Of v I m yes, US plus d m, okay, plus d t I. Okay, do you see what I've done here? So I've split the sum of the over the coordinates into two parts. So one going from 1 to the number of independent parameters, and then the other one going from the number of independent parameters plus 1 up to the total number of the generalized coordinates. Okay, and then of course what did I do? I only enforce my constraints into the dependent coordinates. Okay, so from mi plus 1 to n. So this is the part of the expression which is associated to independent coordinates. Okay, from 1 to ni. This is the one associated to dependent coordinates. And that's why it is in that part that I introduce my constraints and not in this one. Okay, because these are independent. These were dependent, and here, of course, I use my constraint equation to express the dependent in terms of the independent. Okay. All right. So let's continue here. When here I have a double sum to n. Yeah. Plus the sum going from n equal to ni plus 1 n okay. I just distributed the sum. Now what I do, okay, is basically rename this index. Okay, so this index here, okay, these indices S and M, they are said to be mute. What does it mean, mute? It means that once you complete this sum operation, they do not appear anymore, okay, in the final quantity. So what is the only non-mute index here? It's I, right? Because it's the only one which eventually appears in our final quantity. Okay, so all the others I can rename it as I want. I can, as long as I do the correct sum, I can call it, if its name was S, I can call it Z, for example. It doesn't matter. Because eventually, once I conclude the sum operation, it disappears. Okay? So what I do now here, you will see, is basically change, reverse these two indices. So this one I call M, and this one here I call S. And I do this for a reason. You will see. Okay, so here we have the sum, again, of M from 1 to Ni, of V Mi, U con M, plus the sum of M going from 1 to always Ni, you see. Here I'm just changing the name of the index, but the end of the sum has to be the same, of course. Okay, and then I do the same for this one. So here I'm calling it S going from Ni plus 1 to N. Okay, and here what do I have to do? Of course, I have to reverse the name of the indices. So this is going to be VS I. Okay. Here I'm going to have C S M. Okay. U M. And this stays, no, I change it also this one. S going from N I plus 1 to N. And so here I'm having VS I, DS plus VT I, and then I continue. Do you see why I did that? Because now here I had US. Now here I have UM, and that's the same as here. So I can regroup this, okay? I can group this one and this one, putting in evidence UM. So that's what I'm going to do right now. So this is the sum of M going from 1 to Ni of what? Of Vm, okay, plus this sum here. So the sum of S going from Ni plus 1 to N of CSM, sorry, there was a VS, VS I CSM, all of this multiplied by U con M. You see? I put this in evidence. Reversing the order, this US became U con M, and now I can put it, in evidence. And the rest basically stays the same. So this is another parenthesis. S equal Ni plus 1 to N of VS I DS plus VTI. And this eventually, and that's the end of it for now, is the sum of m going from 1 to an I of Vi m u m plus VTI. Okay? So basically, I called all of this between the first bracket Vm without an overhead, and all the second term VTI without an overhead. Okay? Is this clear? Now, tell me when can I slide. This VMI, they are called partial velocity vectors. Okay, and they are the real key of this formulation. Okay, so the VIM vectors are called partial velocity vectors. Okay. Now we use this reformulation. We basically were able eventually to write what? The velocity per point, or a body actually, in terms of this partial velocity vector and motion parameters. Okay, this is what we did. Now we use this one in this expression of the velocity of p dot in the expression of the virtual work. Okay, so we use our new definition of p dot I in the expression of delta W. Okay. So we have that the virtual work, the variation, okay, the virtual variation of the work is the sum of E going from 1 to the number of bodies times the sum of J going from 1 to n of the forces Fi times the partial derivative with respect to the Qj of P dot I, we should have, no? But now we have that P dot I is the sum of m going from 1 to ni of V m I u m plus V T I. All of this multiplied times delta Q J. Okay. Okay, so we just inserted it inside our formulation. Yes, correct. Thanks. Now let's put this sum here. Okay, we can basically transport here in front. Okay, because these two quantities here do not have an m index. Okay, so I can just put it in front. It makes no change, makes no difference. So what I'm having here is the sum of I going from 1 to MB times the sum going from 1 to n times the sum of m going from 1 to ni of f I times v mi and the derivative of um over the qj dot times delta qj. Now, when I do this, please note one thing. You see, I have applied this partial derivative only on the u con m. But the v con m is in front here as a coefficient, and the vti is basically disappeared. Do you remember why? Because when we introduced here, bear with me, just a second. Here, when we define the motion parameters, we said that this was just an a, j, m function of q and t. Do you remember? This one here was only a function of q and t as well, okay? The only dependence on the velocities was such that it was included in the UM. So the motion parameters are defined in such a way that only this one is a function of q, q dot, and t. Okay? We defined it the previous lecture. That's why when I'm going to operate that partial derivative with respect to the q dot, the only term that includes a functional dependence on the q dot is the um, not the vm or the vt. Okay? Because you see, these vi and vt here are just a rearrangement of these coefficients, which do not depend on q dot. Okay? So here, when I have to do this, I only do this derivative on the um. This one stays in front as a coefficient, v con m, and the vt is basically vanishes because it has no dependence on the q dot. Okay? Now, one additional rearrangement that I do is the following. I split, okay, this j into two sums, one going from 1 to ni, and the other one going from from ni plus 1 to n, as I did before. That's to say, I do the following. So the number of bodies going from 1 to mb. The number of coordinates going from 1 to ni, you see. And then also m going from 1 to ni of all of this, which I write here. Plus the second term. Okay? Let me write it a little bit smaller. Okay, you see, I basically rewritten the same thing, but in this case, j goes from 1 to ni, and then from ni plus 1 to n. You see, I just split this sum into two terms. Okay, one going from 1 to ni, and the other one going from ni plus 1 to n. That's all I did. Okay, so it doesn't make any change from the formal point of view, but please now note one thing. Okay, so this j here is basically the number of the coordinate, generalized coordinate. Okay, you see it's the qj dot. Now, this one, basically, this sum here, this component, this part of the equation is relative to the independent coordinates. You see? Because please remember that here we are expressing the constraint equation in terms of the q dot, okay, in the velocities. Okay. So here we are talking about the q dot, which are independent because they go from 1 to ni. Okay. While here, the qj's dot, which appears in this second term, are those going from ni plus 1 to n, which are dependent. Okay? So, this derivative here is the derivative of the um, the motion parameters, which are independent by nature because they have been expressed in terms of the constraint equation. Okay? So we have included the constraint equation into the formulation. So these which appear here, are all independent. Okay. In fact, if you see, they go from 1 to ni. Okay. So these are the independent parameters, the independent motion parameters. While these qj dot are the dependent ones. Okay. So what is the dependence? Bear with me for this second. What is the dependence of the motion, the independent motion parameters with respect to the dependent parameters? It's 0, right? Because these are the independent motion parameters. What is the functional dependence of these quantities with respect to the dependent velocities? 0. So all of this second term is 0. Okay? So this is 0. So we are left only with the first part. So we are left with bodies okay. Now, what we typically do is the following. We only maintain these two sums of fm times the partial derivative. We lost one term here, sorry. We lost this dm, dmi. So here we have okay. It was in front. So we define this new vector f, where fm, the m component, is the sum going from 1 to the number of bodies of fi V on mi. Okay? Let's see. Should be here. Okay, it's just by definition. So in this sum, this part here, this sum between two terms in I, we redefined it. So we basically have only a dependence on the two indexes m and j. So in matrix form, we are almost done. We can basically write the following. All of this must be equal to 0, of course, no? So this is the virtual variation of the virtual work must be equal to 0. This we have seen it, with the virtual work theorem. So we can rewrite all of this. F is a vector transpose times U. It's a matrix. Delta Qi equal to 0. Okay? So this is 1 times Ni, because it's transpose, you see. This is an Ni times Ni matrix, and this is an Ni times 1 column vector. Of course, it's Ni times 1, because this is only the vector of independent coordinates. Okay? This U matrix is nothing than basically the Jacobian. Okay? It's basically the V1, okay? The components of the vector V, partial velocity vector, with respect to the Q dot 1. And then here we arrive to the V1 with respect to the Q Ni dot. Here is the Vni with respect to the Q1 dot. And here we have the Vni, the derivative with respect to the Qni dot. Okay, that's our matrix U. It's basically this term here. Okay. The last two passages, and then we're done. Now, since the delta Qj are independent, okay, we can basically do the same trick. So we pass from here to okay, that's a vector, of course. Okay, that's the typical thing, no, that we do when we pass from a scalar equation to a system of vector equation. Now, since the U matrix represents the dependence of the the independent with respect to the generalized velocities, it must be non-singular, okay? Of the independent, the independent with respect to the Qj independent. Okay? Since this is true, it must be non-singular, okay? Are you with me on this one? So the U, sorry, matrix, which is this one here, you see, it represents the dependence of the partial vectors, of the partial velocities, with respect to the generalized velocities, the independent partial velocities with respect to the independent generalized velocities. So it must be non-zero, it must be non-singular, okay, by definition of independent parameters. So this is non-singular, so we can pass from this one to this one. Okay. Because U is the, you see how is it done? No, you're correct. No, sorry, you're correct. It's here that I made a mistake. This is not the V, this is the U. Sorry. Okay. Okay, it didn't make sense. So yeah. Sorry. So this is the final form of Keynes equation, or in components, componential form if you want, Fm going from 1 to the number of bodies okay, it's either this one, this is the vector form, or this one. Okay. Now, very last passage of the lecture. If we make a simplifying hypothesis, okay? Because this is going to be instrumental for the exercise that we will do next time. So, simplifying hypothesis 1. All the Q all of the Qj's are independent. You remember in our exercise of before of the mass rotating, we had only two parameters, okay, the distance from the origin and the angle, and they were both independent. Okay. This means that if all the Qj's are independent, the constraints equation are such that CMS is equal to 1 if M is equal to S, or CMS is equal to 0 if M is different from S. MB and D m is equal to 0. This one comes from where? Did you remember? Do you remember when we arrived here? We implemented the constraints equation in our formulation here. If all of the constraints are independent, so this if all the general constraints are independent, this equation here basically is an identity. Okay, because you don't have to implement anything. Okay, if all the generalized parameters are independent, you have to implement no constraint equation, as we didn't implement, in fact, no constraint equation in the previous example. So this becomes an identity. And when it does become an identity, it becomes an identity when this is always 0, and this is 1, or when it's the diagonal term, or it's 0 otherwise. Okay, this is what I've been writing in the last term, the last slide. Okay. So this is the simplifying hypothesis 1, and then there is the simplifying hypothesis 2. We choose the generalized velocities as motion parameters. Okay. And this means, again, if you go and check, that in our previous formulation, AJM is equal to 1 if M is equal to J. AJM is equal to 0 if M is different from J. And BJ is always equal to 0. Okay? If this is true, and that's the last part, then Keynes' equation become simply the sum of E going from 1 to the number of bodies of Fe minus P dot I times the Pi over the Qm equal to 0, which is in fact where we started from. Did you remember? Now, next time, we will make an example and to let you see how powerful these equations are. Okay. That's all. All right. So I will interrupt the record.